Okay, so what this video is going to be about is kind of the first major result um, after we talk about the fundamental theorem, and that's going to be Green's theorem. Okay, and so um, Green's theorem is a pretty significant theorem because it relates the line integral around some curve with the double integral of the region bounded by the curve. Okay, so what I mean is if we have some simple closed curve C, then this in here would be our region C. Okay, and so Green's theorem is going to relate the line integral around C with the plane double integral in D. And so the only other thing that's kind of important is that Green's theorem mentions positive orientation, and so positive orientation is just a single clockwise, counterclockwise traverse of C. And so what that would mean would be if kind of we started right here, we would go this way. So that would be positive orientation. If, on the other hand, we kind of thought of going in the other direction, we wanted to go this way, that would be negative orientation. But we're not going to be as worried about that. For the most part, we're going to be concerned with positive orientation, which is just counterclockwise. Okay, so those are the kind of main things we need to talk about before we look at Green's theorem. So kind of without further ado, let's just take a look at what the theorem says. Okay, so this is the statement of the theorem. It says that if C is a positively oriented, counterclockwise, piecewise smooth, simple closed curve, so it doesn't intersect itself anywhere except at its initial and terminal points, and D is the region bounded by C, then notice that if P and Q have continuous partial derivatives on a region containing D, then we have this equality right here. I'm going to make that a little bigger first. Okay, and so it says that the line integral of P dx and Q dy is equal to the partial of Q with respect to x minus the partial of P with respect to y, and it's the double integral over that region. So that's pretty much the whole. That's Green's theorem kind of in a nutshell. Okay, and so before we kind of look at a proof of this, let's take a look at kind of, let me see if you might recognize something. Okay, so let's take a look at these two equations. Okay, so we have so notice if we call this the left-hand side of both equations, call this the right-hand side. Then notice on both left-hand sides involve derivatives. And so what I mean, we have f prime, we have the partial of q with respect to x, and we have the partial of p with respect to y. And both left-hand sides integrate over a region. Okay? So you kind of see, this is kind of the one-dimensional case, and Green's theorem is kind of the higher dimensional case. So in those cases, we're integrating some derivative functions over a region. And then notice both right-hand sides involve the function. And what I mean is we have f, and we have p, and we have q. We don't have the derivative. And notice that both right-hand sides only concern the boundary. So right here, we're just worried about the boundary of the endpoints. So this is over the interval AB, and so the boundary would just be the point A and point B. And here, we're integrating over the entire boundary of that region D. So this, again, this is the boundary of D. Because remember, that's kind of how we define space. And so, kind of the whole point is that Green's theorem is like a higher dimensional extension of the fundamental theorem of calculus. And so, whereas before we integrate over an interval and we evaluate it at the endpoints, now instead of integrating over a whole region, we can just evaluate at the boundary. Okay, so let's take a look at a kind of one example of a proof of Green's theorem. Okay, and so to prove it kind of for the general case is actually really tricky. And so we're just going to look at the proof over what we call a simple region. Okay, and a simple region D is one that is both type 1 and type 2. So in other words, we can express D where x is bound between two numbers and y is bound between two functions of x. And then we'll call this one f1 and we'll call this one f2 of x. And it also can be expressed as a type 2, which would mean that y is between two numbers and x is bound between two functions of y. Okay? And so if we have a simple region, then we can actually prove Green's theorem pretty direct. Okay, so that's kind of the only assumption we have to make right now. Okay? So what we're trying to prove, we want to show that the integral over C of P dx plus Q dy equals a double integral over D of dq dx minus dt dy dx. That's kind of our goal. And we can do that by showing if we show that first integral on the left equals the second integral on the right, and the second integral, so we have to show and the integral of q dy equals if we show this, that would establish our result. Okay. So, if we kind of think of this as equation 2, and this is equation 3, then we can come through and we're going to establish these kind of separate. Okay? So we're going to start to show equation 2 we want to think of D as type 1. So that means that D is the collection of points x, y, where x is bound between two values, and y is bound between two functions. Okay. Okay? And so that means that we can actually evaluate this double integral directly kind of, just using as an iterated integral. Okay? So the integral over D of dp dy over dp dy dA, well, if we want to do this as an iterated integral, we can integrate with respect to x from a to b, and after we integrate with respect to y, x1 of x, x2 of x. Okay? But notice that we're integrating with respect to y after we differentiate with respect to y. And so what this is going to turn into is the integral from a to b of d of x1, evaluated from f1 of x up to f2 of x. Also kind of just using the fundamental theorem, we're going to have the integral from a to b of d of x f2 of x minus d x f1 of x Okay. Okay, and so we've kind of worked with the right side of that equation 2. So let's kind of take a look at how we can evaluate that line integral, that left side of equation 2. Okay, so the left side of equation 2 is dealing with the integral over c of t dx. Okay, and so what I want to do is kind of think about what our region could possibly look like. So we know that y, our values y are bound between two functions, f of x. So maybe this is f2 of x, Let me redraw that. It says we assume it's kind of a type 1 and a type 2, so let me see if I can get one that would be both. Okay, so maybe we can kind of imagine this being a type 1 and a type 2 region. So maybe this is F2 of X, and this is F1 of X, and here's A. And so it's a little kind of funny to think about if we wanted to also do it as a type 2, but we know we can maybe break it into some piecewise pieces. And do that, we can be pretty general about it. So anyway, we have this kind of region here, and our boundary here is going to be C. So we're trying to integrate along this boundary C. In order to do that, we're going to kind of break it up into two pieces. Okay? So we have C1, C2, C3, and C4. And so this integral is just going to be equal to the integral over each of these pieces. Okay? And so notice that for C1, we can parameterize using x equals x, and then y just equals f1 of x. And x goes to negative. Okay, so that would parameterize this curve right here perfectly. So it would start here, C1, at the beginning of C1, and go over to C2, or over to this endpoint. Okay? And so then our integral C1 of p dx, well, that's just going to be the integral from A to B of p of x, y, dx, which is going to, when we kind of fully switch to our parameter, that's just going to be integral from A to B of p of x, f1 of x, and it's not dx because dx equals dx. Okay, so the integral over C1 is going to be kind of this value here. Okay, and let's kind of look at C3 because we kind of think of doing the same thing. So for C3, we'll notice that with C3, our orientation is going to take us this way. So if we want to start over here, end over here, then we want kind of our parameter to be negative x, because we want it to go in that direction. Okay? So we're going to we'll say x prime equals negative x, and then y prime for our parameter, well, that's going to be f2. Okay. And since we have that negative x, x is still going to vary from A to B. Okay, and then for the integral over C3 of p dx, when we switch to our parameters, we're going to have A, B, f of x. t of xy dx. This is going to be an integral a to b t of x f2 of x times negative dx. Because of that negative. We can kind of distinguish it negative integral f of b. Okay, so we've got this one, and we've got this one. So let's look at C4 and C2. Notice that for both C2 and C4, for our parameterization, for C2, we know that x is just going to be equal to x. And for C4, x is just going to be equal to b. Y is going to be some function of our parameter t for both of them, and we'll just call it mu t. But x is going to not vary, because notice that both of those are vertical segments. So no change in x for either of these. Okay? So both are vertical segments. And so for both, x is constant. So dx equals 0. What am I talking about? Equals 0. And so the integral over C2 of p dx is going to equal the integral over C4 of p dx. It's just going to be equal to 0 because dx. Okay, so what does this all mean? Well, we already saw this integral of p dx is going to be equal to the integral over C1 of p dx plus the integral over C3 of p dx. And we can ignore C2 and C4 because both of these are equal to 0. And so we already computed what the integral over C1 of p dx was, and that was the integral from a to b of p x f1 of x dx. And then the integral over C3 was negative integral from a to b of p of x f2 of x dx. And so if we just factor out a negative and write as a single integral, now we're going to have p x f2 of x minus p of x f1 of x dx. And if you recognize this, it's because from all the way back up here, we saw that the right side is equal to the negative of that. Notice we don't have the negative sign up here. We don't have that negative sign. Whereas we do have that negative sign here. And so what that tells us then is that therefore the left-hand side, which was just an integral over c of t dx, equals that negative, because we don't have it, times the double integral over our region D, which is what we set out to show. So this is exactly equation 2. And so, in order to establish equation 3, which was that integral of q dy equals the double integral, this is supposed to be the line integral over c, the boundary, equals the double integral over d of dq dx with respect to area. In order to establish this, you treat D as a type 2 region. So D would be the region where y is between two values, and x is between two functions of y, and you pretty much repeat the same process. And so I'm not going to go through that right now because, like I said, it would literally be the same process. But that's what it would look like. And so once you go through and do that, you would kind of come back to this result that Green's theorem. Okay? So let's take a look at just kind of putting Green's theorem to use a little bit. Okay, for a couple of brief examples. Okay, so we want to evaluate the following integral, where C is the region consisting of the line segments from 0, 0 over to 1, 0, and then from 1, 0 up to 0, 1, and then from 0, 1 down to 0, 0. So we have C here. And notice to set up this line integral, we have to kind of think of breaking this up into a C1, a C2, and a C3. And that would get kind of painful. But if we just use Green's theorem, we can evaluate the integral over this region C. Okay, so what Green's theorem tells us is that this is going to be equal to the integral over d of the derivative with respect to x of our q function, which is going to be xy, minus the derivative with respect to y of our t function, which is x to the fourth, and then evaluate this with respect. Okay, and so notice when we take the derivative with respect to x of this, we're just going to get y. And the derivative of x to the fourth with respect to y is 0. So this whole thing is just going to be a derivative of y with respect to x. Okay? And so we'll kind of think of how we can express C as a region. Luckily, this is one we could do as a type 1 or a type 2. I think maybe for convenience sake, we'll just say that X goes between 0 and 1, and Y goes between 0 and the line right here, which would be the line Y equals 1 minus X. So we're kind of integrating this way. 1 minus X. Okay, and so we can evaluate this interval directly. Okay, so we integrate with respect to y, we're just going to get y squared over 2. Okay, and so then we can plug that in, and we'll have the interval from 0 to 1 of 1 minus 2x plus x squared. That's after we square it. That's going to be all over 2. Yes. I think when we evaluate this, we should get, that's going to be 1/2, so that's going to turn into x over 2. That's going to be minus x, so that would turn into minus x squared over 2. And then we have plus x cubed over 6, because it's over 2, and then it's also going to be over 3 after we integrate. We're evaluating this from 0 to 1. So I think we'll have 1/2 minus 1/2 plus 1/6. Okay? So that was the case where it was easier to evaluate the line interval by switching it to the double interval. Okay? Let's take a look at this one. Okay? So this one, notice if we wanted to parameterize C, we could probably think of 3 cosine theta equals x, and 3 sine theta equals y. And so you can confirm independently that that would parameterize this circle, but imagine trying to carry out that integration. It would just be really, really terrible. Okay, but luckily, we can use Green's theorem. And so again, it's going to be our Q function, which is going to be over here. And we're going to take the derivative of that with respect to x. And then we're going to have minus the t function with respect to y, the derivative with respect to y, of the t function, 3y minus e sine x. And so, luckily, the derivative of this whole thing with respect to x is just going to be 7. And the derivative of this whole thing down here with respect to y is just going to be 3. So we're going to end up having just 4 times the double integral of that region x. So remember, we said that D was the region x squared plus y squared less than or equals 9, because it's bounded by the circle x squared plus y squared equals 9. And so we can rewrite this in polar r theta, where r goes up to 3, theta goes from 0 to 5. So we're pretty familiar with doing that. And so this interval is going to turn the interval 0 to 2 pi, and integral from 0 to 3, and remember we're going to have r dr dθ. So that's what dA equals. And so we're going to have 4 times 0 to 2 pi d theta times integral 0 to 3 r dr. Should be 4 times 2 pi times r squared over 2 evaluated from 0 to 3. Which I think this took out to be 36 pi. Okay, so with these first two examples, we turned. Let me go back to right here. In the first two examples, we took the line integral of t dx plus q dy, and we turned that into the double integral. But sometimes we might want to go the other direction. In other words, for those examples, it was easier to compute the double integral than it was to compute the line integral. And what we're going to look at now is the case that's not always the case. So there's sometimes we might want to go in the other direction. Okay, and one possible application of that is area. So remember, area just equals the integral over a region of the function 1 dA. You know, we also kind of just saw it written as the integral of dA over the region, but it's really over that function 1. And so what that tells us then is if we can kind of figure out a way to make this equal 1, well then the integral over that well, that's just going to be equal to the area. We also know that that's going to be equal to the line integral. Okay? So in other words, we just have to kind of think of some ways to make sure that this is true. And so some examples. Well, if we declare that P of x, y equals 0, and Q of xy equals x, then dq dx minus dp dy equals 1 minus 0. That equals 1. Okay? Or we could have that p of xy equals negative y, and q of xy equals 0, and then dq dx minus dp dy would equal 0 minus the negative 1, which would equal this. Or we could also have p of xy equals negative 1 half y, and q of xy equals 1 half x, And so here, dp, dq dx minus dp dy, q dx minus dp dy would equal 1/2 minus -1/2. So in any of all three of these cases, you kind of have case 1, case 2, and case 3. In all three cases, that function equals 1. And so what that tells us then is that we can find the area by evaluating the line integral where, for example, t equals -y and q equals 0. So that would be -y dx. Or we could evaluate the line integral where q equals x. So q equals x and y equals 0. And so that would be x dy. Or we can evaluate the line integral where p equals -1/2 x where p equals -1/2 y and q equals 1/2 x. And kind of come up with this neat formula for area. So we actually have 1, 2, 3 different formulas for area, the area of a region, by evaluating the line integral along its boundary. Okay, so let's take a look at an example of that. Okay, yeah. So here are the formulas just written a little more neatly. And so we have the line integral over c of x and y, or the negative line integral over c of y dx, or we have that kind of that nice sum there at the end. Okay, so let's find the area enclosed by this ellipse. Okay, and so we could integrate over this region. But let's test out. Let's use that formula. That we just kind of cooked up, where we said 1/2 integral of c of x dy minus y dx. Okay, and so c is going to be this ellipse. And the way to parameterize that ellipse is to say that x equals a cosine t and y equals b sine t. And again, you can confirm independently that that will parameterize that curve. And here, t is going to go between 0 and 2 And so, kind of in specific, if x equals a cosine theta, x equals a cosine theta, or cosine t, then dx is going to be -a sine t. And y equals b sine t, so dy is going to equal b cosine t. So our area is going to equal 1/2 of the integral from 0 to 5 times x, which is a cosine t, times dy, which is b cosine t, minus y, which is b sine t, times dx, which is negative a sine t. We're just going to put down to be 1/2 integral of 0 to 2 pi. And we're going to have a b cosine squared t, and this is going to turn into a plus a b sine squared t dt. DT. Hopefully you can recognize that we can pull that AB out. We have the integral of 0 to 2 pi. When we pull that AB out, we're going to have cosine squared plus sine squared, which equals 1. So we're really just integrating dt, which is going to be AB over 2 times 2 pi minus 0, which is just going to be AB pi, which is the formula for an ellipse, the area of an ellipse. Okay? Okay, so before we do 2 more examples, let's kind of look at how we can extend Green's theorem. So what we've done so far is we've established it for simple regions. And so what simple regions look like? You know, they're not convex anywhere else. So that's not really a simple region. Let me just kind of draw kind of a general blob shape. Okay, so we have a simple region here, and to extend to other regions, we just think of, let's say maybe we have some kind of crazy looking region here. Okay? All we have to think of doing is break this region into simple regions. Okay? So maybe what I mean by that is we could probably break it right here, and then maybe we could break it like right here. So we kind of have D1, D2, and D3. And so D would equal D1, D2, D3. But the question is, let's take a look at the boundary. So we have our boundary here, C. And our question is going to be, will the boundary still be the same? So let's look right here. At D1. So if I call this C1 and I call this C2, then the boundary, so we want to show that the boundary of D equals C. Because we know that the boundary of D is going to equal the boundary of D1 union the boundary of D2 union the boundary of D3. And so we want to show that that is in fact going to be C. So the boundary of D1, if we say that that's going to be equal to C1 union C2, then notice that the boundary of D2, we can start right here. We'll call this C3. We'll call this C4. And we'll call this C5. So the boundary of D2 is going to be, we started there at C1, or we started there at C3, right here, and went this way. So we have C3, union C4, union C5, union, and now we're going to have negative C2. Okay, and kind of likewise, the boundary of D3 is going to be equal to, let's start right here and go this way, and go all the way around here on 1/3 of this way. I call that C6. So we have C6 union. Again, we have to go negatively along C4. So we're going to union negative C4. And so then, when we look at the boundary of D, when we union all these up, well, we're going to have C1, and then we're going to have C2, but we're also going to have negative C2 here. And so those are going to cancel out. So next it's just going to be C3, and then C4. Nope, because we also have the negative C4 here. So we're going to use C3 to C5. C6. I got that the order wrong. I'll do it different. One, two, three, five, six, seven. So the order is not quite right, but we can see that this is going to end up being the only pieces that are going to be left are going to be the pieces along the outside. So in other words, those interior boundary pieces cancel by orientation. Okay. So let's look at an example of kind of integrating over a slightly more technical region. Okay, so what this looks like is this is the boundary of the semi-annular region in the upper half plane. So we're bound by a region here looks like this, and our boundary here. That's what we're trying to integrate along. And as you can imagine, that would be a terrible integral to set up as a line integral, but we can use Green's theorem, because notice that if we split kind of in the middle here, well then this becomes a simple region, and this becomes a simple region. And so we know we can integrate over the whole union. So I think when we integrate, this is going to be equal to the double integral over d. And remember, it's going to be our q function differentiated with respect to x. So 3xy minus our p function differentiated with respect to y. Y. Okay. And so notice that when we carry out this differentiation, we're going to have the derivative of this with respect to x is just going to be 3y, and the derivative of this with respect to y is going to be 2y. So we're just going to have integral over d of y dx. Now notice, again, we can express D as a polar region. And so, in this case, theta just goes between 0 and pi, and r goes out to 4, but it bounds down at 1. And so this integral is going to be equal to the integral from 0 to pi, and the integral from 1 to 4, and y equals r sine theta times r dr. Split this up. So the integral of sine is going to be negative cosine. The integral of r squared is going to be r cubed over 3, evaluated from 1 to 4. No, excuse me. Let's look back up here. I made a mistake. So, this isn't going to be up to 2, or up to 4, it's just going to be up to 2. Because r squared equals 4. R equals 2. And so we're only going to be integrating up to 2 on these. Okay, and so cosine of pi is negative 1, cosine of 0 is 1. And then we're going to have x squared plus 2 cubed is 8, and 1 cubed is 1. And so we're going to have 2 times 4, 7/3. Which is going to be 14/3. Okay, now let's look at one more kind of extension, and then one more sample, and then we will be done. Okay, so now we want to extend Green's theorem one more time to a region that has like a hole in it. Okay, so we kind of imagine that we have a hole, and so this is our region D. And notice that the boundary of D equals kind of two pieces. We have the outer piece and we have this inner piece. And the boundary is going to be the whole thing. Okay? So, how can we extend that? How can we get there from a region without holes as we can kind of think of breaking it into two regions? So maybe we'll we'll call this one D1 and this one D2. So notice that the boundary of D1 oriented this way is going to give us kind of the top half of C1 and the top half of C2. And then when the bottom one, when we find the boundary of D2, notice right here, we're going to be going back the other direction. It's kind of just like before, the boundary of D1 union the boundary of D2 is going to equal, well, we're going to get the top half of C1 and we're going to get the top half of C2, and then this piece here and this piece here are going to cancel because we're taking the line integral in both directions. And so that's going to end up just equaling that boundary. And so kind of like we did, just like we did kind of with the bring in the smaller regions, now we can break pieces with holes into smaller regions. Okay? Okay, let's wrap up with this kind of last example. Okay, so we're given here this force, this vector field, f of xy equals, and kind of, it has it written in the I, j component, but if we kind of write it, we have negative y over x squared plus y squared, and then we have x over x squared plus y squared. And we want to show that this integral equals 2 pi for every positively oriented simple closed path that encloses the origin. Okay? So in other words, we have the origin. We just want any random path positively oriented and encloses the origin. We want to show that the integral over that okay? So that's kind of our goal. And so the way we're going to do that is we are going to kind of randomly start with just an easy circle. We're going to call this C2. We're going to orient it the other way. And so notice then we define this region in here. It's between those two curves. Okay? And so we know then that the integral over C of FDR Okay, so let's take a look. We can apply Green's theorem to this region D. And so that would say that the integral over C of P dx plus Q dy plus the integral over C2 of P dx plus Q dy. q dy is going to be equal in the integral over that region d of d q dx minus dt dy dx. Okay, so this is by Green's theorem. Because the boundary of D equals C union C2. The boundary of this region D is both of these pieces. Okay, so that's why we integrate over both pieces. And it equals a double integral over that region D. Okay? But notice if we go back right up here, this is going to be our P, and this is going to be our Q. And so the derivative of P with respect to Y is going to be when we work through it and calculate these derivatives, we're going to get y squared minus x squared over x squared plus y squared. So that's when we differentiate.
Casey Jackson and Matthew Seminole, please come to the attendance room 205.
When we differentiate this piece with respect to x, we have to use the quotient rule and we'll end up with y squared minus x squared.
Zach Fitzgerald, please come to the attendance room 205.
And when we differentiate p with respect to y, we're going to get y squared minus x squared over x squared plus y squared 1 squared, which just equals zero. So that whole thing just equals 0. Okay? And so what that tells us then is that the integral over c of p dx plus q dy equals, plus the integral over c2 of p dx plus q dy equals 0. And so the integral over c of p dx plus q dy equals negative the integral over c2 of p dx q dy plus. Okay? And we can rewrite this. Hopefully we can recognize this. This is just the integral of that.
Casey Jackson and Zachary Fitzgerald, please come to the attendance room 205.
Okay? And so now all we have to do then we want to show that this equals 2 pi. So all we have to do is calculate this and show that this equals 2 pi. So let's take a look at that. Negative integral of C2. Okay. Well, remember C2 here is the negatively oriented circle of radius A. So this has a radius of A. And so C2.
Joshua Spentak, please come to the attendance room 205.
The negatively oriented circle of radius A. And that tells us that negative C2 is just the circle of radius x. Okay? And so we know then also that negative integral of C2 is going to be equal to the integral of negative C2 of f dr. But negative C2 is just the circle of radius x. And so we can parameterize this as x equals a cosine t, y equals a sine of t, t goes to 0, 5. So this is going to be equal to the integral of from 0 to 2 pi. And when we express f as f was negative y over x squared plus y squared and x over x squared plus y squared, so we're going to have negative a sine of t over a squared cosine squared t plus a squared sine squared t. And then we're going to have a cosine of t over a squared cosine squared t plus a squared sine squared t. Dotted with the derivative vector, which will be negative a sine of t and a cosine of t. And so when we carry out this dot product, everything is going to be over a squared cosine squared t plus a squared sine squared t. And we're going to have negative a sine t times negative a sine t plus a cosine t a cosine t. Okay. And notice then that we actually get which is just all of that just reduces to 1. So we just 0 to 2 pi dt, which equals 2 pi. And so we kind of use this crafty technique here. Oh, that's not at all what I wanted to do. We use this crafty technique by putting this inner circle in here and defining this region, and then showing that the integral kind of be the same, that for any, this is true, simple closed, curve, being about this. Okay, so that's everything for Green's theorem. It was quite a bit, but I hope that was helpful. And so, the main thing is Green's theorem. Ready?